Okay. Okay. We'll start. We'll start. Good afternoon, all. Online students, can you confirm whether I'm audible? Right. Online students, can you confirm whether I'm audible for both Zoom and YouTube Live? I'll also check from my end. Am I audible? Yes, ma'am. Right. Okay. Good afternoon again. Uh, can you drop me a quick response whether I'm audible? Right. I check from my end that I'm audible. Others from both Zoom and YouTube, am I audible for both of you? So you have disabled the chat. Let me check. You are saying Zoom chat. Now it's okay. Sorry about that. Sorry about that. Now the Zoom chat is working, right? Can anyone drop a message and check whether it's working? Right? Sorry about that. The Zoom chat was disabled. Now I enable the chat. Yes, me. Right away. Thank you. Okay. Thank you. Right. YouTube also okay, right? Yes. It's okay. Thank you. Thank you. Okay. Listen. So we'll start. Listen. Right. So today, as we planned, we are moving on to the next lesson, next sub lesson in mechanics. Okay? That is hydrostatics. That is hydrostatics. When it comes to hydrostatics, now we are in the very last parts of mechanics. We have two more lessons to be completed in hydrostatics, in mechanics. One is hydrostatics, and the last one is hydrodynamics. So we call fluid dynamics. Right. Now we are in last two units of mechanics. Right. So today we are starting hydrostatics. Right. And today will be the starting day, the starting seminar of hydrostatics. Right. And today the plan is we'll be starting discussing all the fundamentals, the basic theories that you need to know in hydrostatics, right? And we'll be discussing some example calculations, example applications as well, right? So that's the today's plan, right? That's the today's plan, right? Yeah, still students are joining in, but anyway, now it's 3:35 now. I'll start, right? I'll start anyway. If you are joining through YouTube, you can go back and see. But if you are joining through Zoom, you don't have a chance to go back and see. But anyway, I'll start because we plan to start the session by 3:30. Now it's 3:36 almost. Right? So we'll start. Right. So first thing is, since there are new students, right? So I can see there are new students in both Zoom and YouTube. No? Since there are new students, right? I'll put the respective links to both chat boxes in Zoom and YouTube. Give me a second, because since you are asking about the registrations and all that, give me a second. I will first put the right. So in Zoom also I have put the respective details there, right? So if you go to my flyers also, you can get everything, right? And from these communities and other Telegram channels, WhatsApp communities, from all that, you can get the updates about the coming lessons as well, right? For new students, for new students, yes, you can get all updates through my basically through MATLAB education communities, WhatsApp communities, and my Telegram channels. Basically, you can get all the updates about the upcoming lessons, upcoming units, and everything from that. Right? Okay. So without further discussion, now we are going to move on to hydrostatics. Right? Okay. First, let's see what we are going to discuss here as hydrostatics. Right. Now, when it comes to hydrostatics, now let's explain. Let's get this clarified using the verb itself, using the topic itself. What is meant by hydro? Water or liquids, right? Water or that is about liquids, right? Hydro means water. That is correct, right? The basic idea which comes to our mind is about water or liquids. That is means hydro, right? What is static? Right now, if I break this down, right? If I break this down, right? If I break this down, here we have hydro plus static. Hydro plus static. Right? Hydro plus static. What's the idea of static? What's the idea of static? Static. That is not an new word to you know, because from fiction also you have heard about static in whereas center of gravity, static. Right? What is static? What is meant by static? Right? Now, for my questions, all of you can engage answering. Right? Stationary. Correct. Right? Yeah, one says stationary. Yeah, correct. Stationary. Stationary or fixed or static means stationary. Right? Fixed. Right? Now, the idea is hydrostatic means hydro is about liquids. Right? Static means stationary. Right? So, therefore, here we are going to study about liquids at rest. We are going to study about liquids at rest. Right? Liquids at rest. The difference is now basically we have two types of liquids. Like we can have either moving in the sense flowing. We can either have flowing liquids or static liquids. No. In hydrostatics part, we are talking about resting liquids, liquids at rest. And the next part coming up is called hydrodynamics, or we call fluid dynamics. Dynamics means moving. So there we are talking about, there we are discussing about moving liquids, flowing liquids. So in hydrostatics, that is all about static liquids. Right? Is that clear? Okay. As the first point, write down. As the first point, write down. As the first point, write down. First point, first point, write down. First point, hydrostatics is hydrostatics is hydrostatics is hydrostatics is the study on hydrostatics is the study on hydrostatics is the study on non-moving. Hydrostatics is the study on non-moving within brackets static, non-moving within brackets static fluid, yeah? Fluid. What's the idea of a fluid? Next question. What is the fluid? Liquid. Substance. What kind of a liquid substance? What's the idea? Now you can engage answering my questions. What's a fluid? What is meant by fluid? This is actually not a new word to you. In O levels also, we are discussing about fluids. You have heard the word fluids. What is a fluid? What is the fluid? Fluids are not only about liquids. Fluids is the single term for liquids and gases. Liquids and gases. Fluid means any liquid or gas, right? So fluid means liquid or gas. Liquid and gases or gases. Liquids and gases. Fluid is a single term for liquids and gases. So even though we say it's hydrostatic, All these theories are not only valid for liquids, but also valid for gases as well. Liquids and gases. Common word for liquids and gases is a fluid. Right? Fluid. As the second point, write down. Second point. Liquids and gases. Correct. Good. So likewise, engage answering questions. Right. Second point, write down. Fluids are fluids are fluids are fluids are liquids or gases. 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 Right. Look at the board. Look at the board. Now, when it comes to hydrostatics, listen. When it comes to hydrostatics, right, this is not going to have very much links with the previous parts we covered in mechanics. Right? So therefore, so hydrostatics and hydrodynamics, the last two parts coming up, right? Even though you don't have that kind of a solid, a thorough knowledge on previous parts of mechanics, that doesn't matter. If you grab everything from scratch here in hydrostatics, right, you can easily grab all the things in hydrostatics and as well hydrodynamics. So therefore, today I will be explaining everything from zero, from scratch, about hydrostatics. Right? So it doesn't matter how you perform in previous lessons. So earlier lessons in mechanics or hydrostatics. Right? Hydrostatics and hydrodynamics actually. Right? So that's why I emphasize that no prior knowledge is required for hydrostatics. Right? Today we will be discussing everything from zero, from scratch, from A to Z. Right? So therefore, grab everything from the beginning because we are starting the discussion from zero, right? And we are moving towards, always in a lesson, always we are starting from zero and moving towards advanced questions. That is how the flow is in any kind of a lesson. Right? So here also that's same. Now I'm starting the discussion from zero as any student, who is in any level can understand. Right? So understand everything from the beginning, have everything from the beginning, then easily, without any hassle, easily you can move on to the rest of the parts of hydrostatics without any hassle. Right? Because this is not going to have, I'm not saying there are no links that, there are no links. This is not going to have major limits with the other parts we covered in mechanics. Right? Hydro parts are somewhat separated. Right? Okay. So first idea we have is about density. I know most of you know what density is, right? But we will start with this discussion from the beginning, from the scratch, and moving on. As the next heading, write down density. Density. Okay. Tell me the equation of density. Now we are starting the equation of density. We way back in mix and dynamics, right? More than a year back. What's the equation of density? Mass over volume, right? Mass over volume. Good. And MOV, yes, good. And MOV, right? So everybody knows that here. Everybody knows equation of density is mass over volume. Now, density can be written as, look at the board, don't write. Look at the board, density can be written as rho equals MOV. Rho is the notation, the symbol we use for density. So, rho is a Greek symbol. Rho is a Greek symbol. This is not E, this is rho. Rho, right? So, rho is a Greek symbol. Rho, rho. That is called rho. Rho is a Greek symbol. Right? That is the standard notation of a density. Rho. Right? So, basic equation of a density is rho equals MOV, density equals mass over volume. Right? So, everybody knows the equation. Let's take this down. Take down the equation. So especially online students, you can engage with the lesson. You can always engage with the lesson by answering to my questions. I'm looking at both chat boxes in YouTube Live and the Zoom as well, right? Doesn't matter whether you are doing online using Zoom or YouTube, right? Always you can forward questions to me using the chat boxes. I'm looking at both, right? For physical students, you can always forward questions in the classroom, right? For online students also, at any time, if you got a question, right, forward those questions via chat boxes, right? Okay, from introduce terms one by one like this. Introduce terms. First row density. Row density. Simple M mass. Simple M mass. Row density. Simple M mass. Simple M mass and V volume. V volume. V volume. Right? Okay. A small task, very small task. Quickly determine units and dimensions of row. Quickly determine units and dimensions of density. A very small task. Quickly determine units and dimensions of density. Now we have done the same before in units and dimensions as well. Right? Just to recall again, determine units and dimensions of density here. Quickly. Quickly determine units and dimensions of density. Okay, very straightforward, very easy, very straightforward. Units. For units, we are using simple brackets, right? Units of row are units of M over units of V. So units of row are units of M kilograms. Units of V cubic meters volume, right? So therefore, unit is kgm minus 3. kgm minus 3, right? And dimensions. For dimensions, we are using square brackets. For dimensions, we are using square brackets, right? So they are not new things to you. So dimensions of row are dimensions of M, capital M. Dimensions of volume. Volume is the length in width in breadth. L cube, right? So therefore, dimensions of row ml minus 3. ml minus 3. Very straightforward. Right? Okay. Next point. Next point. Listen. Listen. Now, listen. Now, if you are considering multiple fluids, right? If you are considering multiple fluids, still we can determine density. Now, if we have more than one fluid, density is determinable. Right? If we have multiple fluids, density is again there is mass over volume, that is true. But if we have multiple fluids, total mass over total volume, it changes total mass over total volume. If we have more than one fluid. Okay. Then next point, write down next point. Write down next point. If multiple fluids are mixed, next point. If multiple fluids are mixed, 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 put a comma, if multiple fluids are mixed, put a comma and write down the equation below. Any density equation, same equation, if multiple sums, we have to use total mass and total volume. Total mass is total volume. Same equation, a little bit modified for multiple fluids. Take it down and highlight this equation. Take it down and highlight the equation or square equation. Highlight or square equation like this. Right? So we will see an example when mixing multiple fluids as well. Right? So we will see an example, don't worry. Right? So if multiple fluids are mixed, that is total mass over total volume. Right? Very simple as that. Understood? Right. Now let's see an example. What does this mean? Right? Let's see an example. Let's see with an example. What does this mean and how to use this? As an example, write down. As an example, write down. Example. Write down. Example. Write down. If equal masses of if equal masses if equal masses of two liquids if equal masses of two liquids of densities if equal masses of two liquids of densities rho 1 and rho 2 like this, rho 1 and rho 2, rho 1 and rho 2. If equal masses of two liquids of densities rho 1 and rho 2 are mixed together, determine the density of the mixture. 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 Right. Okay, first listen. Right. Now, as I told you, if we have a mixture in the sense, if you have more than one fluid, more than one liquid, we can write density as total mass over total volume. No? Total mass over total volume. Having that in mind, first I will give you 2-3 minutes to try by your own before I explain. And so I will give you like 2 minutes. Right? Now, only data I have given me is rho 1 and rho 2. Then your final answer should be something in terms of rho 1 and rho 2. Right? Write out. Give it a try. This is the hint. If we have more than one liquid, right? Density is total mass over total volume. Right? Total mass over total volume. So you to get a more understanding. Now this is what is going to be done. Right? Equal masses, no? Right? Look at here before, right? Look at here before, right? Here I have one liquid, right? Here I have one liquid of density rho 1, right? And mass equal masses. Let's say M, right? And here I have another liquid of density rho 2, but the same mass, right? These two are going to be mixed together. Into one, and we are going to determine the density of this resultant mixture. Right? If masses M and M are mixed, mass of this thing has to be 2. Right? Two masses should be added because these two are going to be added. Right? So resultant mass or net mass will be 2M. Right? Think of volumes. Right? So before I explain, think of volumes, and now I do this. You better take this down. You better take this diagram and try it out. I will give you 2 minutes. Grab all the things from the beginning. Grab all the things from the beginning. Then uh, easily you can tackle these things in hydrostatics when you have the foundations from the beginning. Right? Sorry? Reaction process. Put your answers to chat box if you have got any answers. Put your answers to chat box if you have got any answers. Put your answers to chat box. Correct. Simplification error is here. Check the simplifications again. Online students, any answers? Now it is correct. Online students, any answers? So if you got answers, you can put them to the chat box. To row 1, row 2, or Rho 1 plus rho 2. Good. Good. Also good. No. Check simplifications again. What is it? Total volume? Total volume is wrong. That's a problem. Total volume is wrong. Okay, let's see. Let's see. Look at the board. Look at the board. I'll give you another question to type. If you didn't get the answer for this question, don't worry, right? Grab this from this question, then I'll give you another question to try again. Right? Okay. Okay, here. Now, according to rho equals MOV. Look at here. Look at the board. According to rho equals MOV, if rho is different, even if masses are same, volume should be different. No? Volumes are different. So therefore, I will assume, listen, I assume these volumes are V1 and V2. I'll assume volume here is V1. I'll assume volume here is V2. Then resultant volume here will be V1 plus V2. No? Is it clear? Clear, right? Clear. Right. Now, look at here. We know rho equals MOV. We know rho equals MOV. If I use this for first liquid, we can write rho 1 equals MOV1, right? And if I use this for second liquid, I can write rho 2 equals MOV2, right? Right? Where the road? Now, if I need density, right? Density is total mass over total volume. Total mass over total volume. So rho is total mass can be written as 2. Total mass can be written as 2. Total volume can be written as V1 plus V2. Total volume can be written as V1 plus V2. But V1 and V2 are not given. V1 and V2 are not given. What we can do is we can convert V1 and V2 to given rho terms using these relationships. Right? Now from the first one, if I subject V1, that is MO1. Right? From this first equation, if I subject V1, that is MO1. Right? Now, if you need to subject this from here, see, now from this, I can write V1 equals M over rho. From this, I can write V2 equals M over 2. Right? Now I'm going to plug those values here. Where the board. I'm going to plug those values here. Rho can be written as 2m over. For V1, I can write m over rho. For V2, m over rho 2. For V2, m over rho 2. Right? Take m out. Because m is common for denominator, then m cancels. If you take m out, m cancels. Simplify. Now this is a simplification. Here we have 2. And this is 1 over rho 1 plus 1 over rho 2. Common denominator is going to be rho 1, rho 2. And here rho 1 plus rho 2. Right? Simplify this. Rho equals 2 rho 1 rho 2. Division is the multiplication with reciprocal. 2 rho 1 rho 2 over rho 1 plus rho 2. 2 rho 1 rho 2 over rho 1 plus rho 2. Right? So we can arrive at the final answer. Resultant density equals net density. Resultant density equals 2 rho 1 rho 2 over rho 1 plus rho 2. Right? Simple as that. Right? The only equation I used was rho equals MOV. This is also rho equals MOV. Here also I have used rho equals MOV. Only equation I used was rho equals MOV. Right? Density is mass over volume. Right? Good. Take it down. Take it down. Take it down. If you didn't get the answer by your own, take it down. And any physical, online, any student, if you have any questions, if you have any doubts, please raise them. Please raise them. No need to keep them in mind. You can raise them. So this is the first question. This is actually an example. This is the first example question we discussed today. Right? First example question. Raise your questions if you have anything. Right? Doesn't matter whether you are a regular student of the class or if you are a new student who just came today for this free seminar. If you have any questions, you can always raise, right? And I'm always happy to answer your questions. Understood, right? Understood, right? Okay. Let's try another one. Let's try another one. Okay. Next question. Now this is example one. Right? Take down this example two. Take down this. Write down equal volumes. Equal volumes. Equal volumes of three liquids. Equal volumes of three liquids. Equal volumes of three liquids of densities densities write down this way of densities D1, D2 and D3, right? Equal volumes of three liquids of densities D1, D2 and D3 are mixed together. Are mixed together. Are mixed together. Are mixed together. Right? Determine the density of mixture. 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 Right? Okay, try it out. So you better have a diagram first. Right? So as I had a diagram before, right? Again, first just draw a sketch, a small diagram. Try it out. Try it out. This is what we are going to do here. We have three liquids, right? Three liquids like this. three liquids. Now equal volumes, right? Equal volumes. Volumes are equal. V and V and V, right? But densities are different. Densities are different. D1, D2, D3, right? All three are going to be mixed together. All three are going to be mixed together, right? All three are going to be mixed. All three are going to be mixed, right? Then volume of the mixture should be 3V, right? So let's assume the density as no. Right? You can think about masses and write it out. This is the diagram you should have. Write out, write out. Write out. So this is actually the this is actually the first type of questions we have in hydrostatics. Right? There are several types. There are more types coming up. This is the first, the simplest type of questions we have. Determining densities. Determining densities. Determining densities. B1 plus B2 plus B3 over 3. Correct. B1 plus B2 plus B3 over 3. Correct. Good. Right. So if you got your answers, you can put the chat box. Total mass or total volume. Right. Now consider these masses as masses are different. M1, M2, and M3. Then total mass is going to be M1 plus M2 plus M3. Since mass is not given, assume it as M1, M2, and M3. Masses are different because densities are different. Different density with equal volumes, no, masses will be different because M equals 0 or O equals M of V. Masses are different. That's the only idea. That's the only thinking, the small thinking you have around here about masses. Others, is the answer same? Are the answers same? Are the answers same? So when it comes to hydrostatics, this is a crucial part in mechanics, right? Very crucial and important part in mechanics. Therefore, grab everything from the beginning. Everything from the beginning. When it comes to hydrostatics, this contributes MCQs, structured essays, and essays. Right? So this contributes all three types of questions in our paper. Right? That's a crucial part, very important part in mechanics. Right? Finished. Shall we check? Shall we check? Okay. Okay. Again, now I'm going to use rho equals MOV. See, now from this equation, first we have to get this formula. You can go. Equation is rho equals MOV. Right? Now volumes are same. Volumes are constant. Volumes are constant. Right? If volumes are constant, when densities are different, accordingly, that should be different. No? Right? When if volumes are constant, when densities are getting different, accordingly, masses should be different with the equation, with the relationship. Right? So therefore, I'll assume these masses as M1. I'll assume these masses as M1, M2, M3. Right? Then if I add all three together, right, mass here has to be M1 plus M2 plus M3. Mass here has to be M1 plus M2 plus M3. That's the only thing in we need. That's the only thing in we need. Yeah. Right? Okay, now we can apply in our equations. We can apply in our equations. Right? Look at the board. Right? So it seems most of you have got the answer. The second question. Look at the board. Density can be written as total mass over total volume. If there is a mixture, there is always total mass over total volume. Right? Density is, let's say, rho. Right? Total mass is M1 plus M2 plus M3 over total volume is 3V. Right? Now, here itself, I'm going to expand. Right? You can do either way up. If you apply this equation 3 times for these three also, that is fine. Right? Or if you expand the terms here itself, that is also fine. Right? Now, since I expanded the terms, since I used the equation separately for the previous question, here I will show you how to expand here itself. Right? Now, I'm going to use the equation again. No? If you are using external equations, mention them here. Now, I'm going to use rho equals M over V. If M is subjected, M can be written as 0. Mention this. M can be written as 0. Mass can be written as volume into density. Mass is volume into density. And with that, I can expand these terms. Then M1 can be written as volume of M1 into density of M1. That is VD1. Right? So this can be expanded as VD1. Similarly, M2 can be written as VD2. M3 can be written as VD3 over whole thing over 3V. Right? This cancels. V is common. V is common. Right? V is common. V2, 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 V. Now, if you take this V out, it will be common and it will cancel. It cancel here in this same line. Now, subject row, this is a simplification, just a matter of simplification. Subject row, that is D1 plus D2 plus D3 over 3. D1 plus D2 plus D3 over 3. Right? Final answer, this density is net density. And density equals D1 plus D2 plus D3 over 3. Right? Understood? Understood? Right? Very easy. Any questions on this? Or online students? Online students? Is it clear? Zoom, YouTube, anyone? Is it clear enough? Is it clear enough? Or any questions? Audio questions if you have anything, right? So I'm looking at both chat boxes, right? Audio questions if you have anything. Clear, clear, right? YouTube students, is it clear? Okay, understood, right? Understood. Good. Okay, next, next question. Write this down. Next question. Write this down. Okay, next question. Write down. Write down. Two liquids A and B. Two liquids A and B. Two liquids A and B. Write down. Two liquids A and B. Two liquids A and B. Two liquids A and B of densities. Two liquids A and B of densities. Two liquids A and B of densities 1000 kgm minus 3 and like this 1000 kgm minus 3 and 800 kgm minus 3. Two liquids A and B of densities 1000 kgm minus 3 and 800 kgm minus 3 are mixed together. Are mixed together. Are mixed together. Mixed volumes of A and B. Mixed volumes. Mixed volumes. Mixed volumes of A and B. Mixed volumes of A and B. Mixed volumes of A and B are mixed volumes of A and B are mixed volumes of A and B are 60 cubic centimeters and 40 cubic centimeters respectively. So I mentioned the values in the board: 60 cubic centimeters and 40 cubic centimeters respectively. And determine 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 density of mixture. Determine density of mixture. Determine density of mixture. Determine density of mixture. Okay. Right. Determine density of mixture. Right. right? And here you will get the density as a numerical value. You will get the density because I have given all data as numbers. You will get the density in numerical value, right? Once you get a value, you can say out the answers. You can share the answers, right? Try it out. Try it out. And once you got the answer, put them to the chat box. Online students and physical students, you can share the answers with me. Got anything? Got it. You? So previous two questions we tried using label. Now I will give this question in terms of values, numbers. I need the answer in standard units. I need the answer in standard units. Right? Now densities are given in kg m minus 3. Right? Kilograms per cubic meter. Now I gave this as cubic centimeters. Right? Check again. And I need the final answer. I need the final answer in the standard unit. In this standard unit. We are determining density. No? Density should be in the standard unit of density. So we all know that standard unit of density is kg minus 3. So at the beginning also we found it out now. If you are converting units, do it properly. If you are converting units, do it properly. What do you think? I'm going to. Check again, there's a small mistake. Check again. Yeah, I see some students are getting answers. Yeah, some say 920 kg minus 3, 920. You also put the same. This should be something with unit conversion, right? In US also, there is something with unit conversion. It seems your number is correct, and not the unit properly. Some has got 9.2, right? So if you have got something like 9.2, that is probably unit conversion mistake. That is probably a unit conversion mistake. 920 is an acceptable answer. That is acceptable. We'll see. Any other answers? Any other answers, other students? Any other different answers? No. Good. Same. Same. Okay, let's see. Time is enough. Time is enough. Let's see. Okay. Now here, now again the same thing. Now from this first liquid, right? We have a volume of 60 cubic centimeters, right? And density is 1000 kgm minus 3, and this is mixed with 40 cubic centimeters of a liquid of density 800 kgm minus 3, right? These two are mixed together, right? These two are mixed together. These two are mixed together, right? Then if a volume of 60 and volume of 40 is mixed, this volume has to be 100 cubic centimeters, right? We don't know the resultant density. I'll consider it as rho. We'll consider it as rho, right? Okay. Since masses are unknown, let here, since masses are unknown, I'll assume that as M1 and M2, right? Then the mass here has to be M1 plus M2, right? Okay, same approach, right? Look at the board. Density equals total mass over total volume. Total mass over total volume. So rho equals total mass is M1 plus M2 over total volume. Total volume 100, but that is in cubic centimeters. Right? Now I'm going to expand these terms here itself using the equation. Right? So we know rho equals M over V. So M is 0. M is 0. M is 0. Right? So rho equals M of can be written as V is 60, rho is 1000. Right? Now I observe something like this. Listen, I observe something like this. In numerator also, I'm going to get volumes in cubic centimeters. And in denominator also, I have volumes in cubic centimeters. So therefore, even if I didn't convert, it cancels. Even if I convert, it cancels. Even if I didn't convert also, it cancels. Because in numerator also, I am getting something in cubic centimeters. In denominator also, I have something in cubic centimeters. So therefore, it's going to cancel, right? Even if you convert total, that is fine. Either it cancels, but if you see that part canceling, no need to count the conversion. You can directly substitute as well, right? Now, if I write with the conversion for your clarity, if I write with the conversion, M is V1, right? M1 is V1, 60. How can we convert cubic centimeter to meter? Centimeter to meter? Centimeters to meters. 10 to the power minus 2. Then cubic means centimeters times centimeters times centimeters. Then 10 to the power minus 6. 10 to the power minus 6. Right? So this is 60 times 10 to the power minus 6 times. Right? Plus this one 40 times 10 to the power minus 6 times 800. 800. Not 8,000, 800. 800. Right? Over 100, 100, that is also in cubic centimeters, and draw minus 6. Right? So that's why I did it. Now, even if I didn't do this conversion, even it cancels. I think it cancels. Doesn't matter. Right? But if it doesn't cancel, definitely we have to do the conversion. Now here since it cancels from numerator, even if you didn't do the conversion, that is fine because cubic centimeters in numerator, cubic centimeters in denominator cancel each other. Right? So that is why this conversion cancels. Then 10 to the power minus 6u, 10 to the power minus 6u, 10 to the power minus 6 cancels. Right? It cancels. Rho equals, now simplify. Rho equals, right? Here 60 times 1000. 60 times 1000 plus this is 40 times 800 over 100. Right? Now you can divide both terms by 100 now. Right? So it cancels again. 0, 0, 2 zeros here, 2 zeros here. Cancels. Right? Now you can easily simplify. Rho equals 60 times 10 remains 600. Plus here 40 times 8 remains 320. Yeah, your answers are correct. That is 920. Now this is in standard weights. 920 kgm minus 3. 920 kgm minus 3. 920 kgm minus 3. Right? Yeah, I saw most of you have got the correct answer. Right? If you got 9.2, that is because of unit conversions. Right? Make corrections if you have anything. Make corrections if you have anything. Make corrections. Make corrections if you have anything. And raise your questions if you have anything, any doubts, any questions. If any one of you need any clarifications about this, raise your questions. Raise your questions. All good? Is it all clear? Yeah. Right? Okay, look at the board. Look at the board. Listen. Another thing important and very important when it comes to MCQ. Right? Look at the board. Right? Now, if a question is given in numbers, as numbers, right? If only two liquids are mixed, right? If only two liquids are mixed, right? Always the density of the mixture comes to a value between mixed densities. What am I going? Now, if two liquids are mixed, different densities, density of the resultant liquid always comes to the density in between densities of two mixed densities. Right? Now we mix 1,800 now. We ended up having 920. Something in between 1,800. That feature is always there when liquids are mixed. Right? Uh, if MCQ kind of a question has come, if you have now, you have five choices, right? If you have answers less than 800 or greater than 1000, they cannot be answers. Definitely, it should be something in between 1000 and 800. Whatever the volumes you mix, always is going to be the value between 1000 and 800. Keep that in mind. Right? Keep that in mind. That is only valid for two liquids. Right? That is only valid for two liquids. If more than two liquids are given, you can do you have to do the calculation and get it done. Right? But when only two liquids are given, now before doing the calculation also, we can have an idea. We are going to get value between these two. Right? Now, the importance of knowing that is even if you made the mistake and if you ended up having an unacceptable value, still if you know that it cannot be something beyond this range, then still at least you have a chance to go back and check whether you have done any mistake. Okay, with the red pen mention this, with the red pen mention this, with the red pen mention with an asterisk mark, put an asterisk mark with the red pen and mention like this. Right? Put an asterisk mark with the red pen and mention like this. When two liquids of when two liquids of when two liquids of when two liquids of different densities when two liquids of different densities when two liquids of different densities are mixed together when two liquids of different densities are mixed together when two liquids of different densities are mixed together, final density becomes final density becomes final density becomes final density becomes a value in between final density becomes value in between final density becomes value in between final density becomes a value in between densities of mixed liquids. Final density becomes a value in between densities of becomes a value in between densities of mixed liquids. Right? Densities of mixed liquids. Right? So this is the example. Since I mixed two densities of 1000 and 800, final density is a value between 1000 and 800, 920. Right? That is how it works. That is how it works. Right? Okay. Any questions up to here before moving on further? Any questions up to here? Online students? Any questions up to here before moving further? Any questions up to here before moving further? Please respond whether you are clear or not. Okay, right? Good. Right. So we are moving on. We are moving on. Next heading. Next heading. Write down effective density. 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 Right. Now stop all your work and listen. Stop all your work and listen. Right. Now, effective density is about something like this. Okay, let's assume we have a water sample here. We have a water sample here. Right? We have a water sample here. Look at the board. This is a water sample. Sample of water. Water sample. Right? A water sample. Right? Sometimes for water or any other liquid also that is possible. Now for the explanation, I consider water. Right? Sometimes for water, air bubbles can be mixed. Have you seen water with mixed particles? Right? Mostly when water is cold, when we have water flow, when water is cold, air bubbles can be seen. Air bubbles means these kind of air bubbles inside water surface, like this. Air bubbles inside water surface can be seen. Air bubbles. They are not water bubbles, they are air bubbles. Right? Air bubbles can be seen. Air bubbles can be seen. Right? Now the problem is this. Listen. Now the problem is this. Right? When air bubbles are mixed, right? What happens is, if I consider particular volume of liquid, right? There is not only liquid particles in that particular volume. But also mixed. In air bubbles, we have air. Air bubbles means they are not the liquid. They are bubbles. So therefore, it causes decreasing the quantity this liquid. Since air bubbles are mixed, because air is less denser than water. Air is very much less denser. Now, usually density of air is around 2 atm minus 3. Usually density of air is around this. Usually density of air is around this. Whereas density of water is 1000. Density of water is 1000. So air bubbles are less denser. So therefore, what happens is when air bubbles are mixed to water volume or any liquid volume, that density of the liquid decreases. Because always density of any air medium is less than liquid medium. Right? Density of any air medium is less than liquid medium. So therefore, when air bubbles are mixed, the resultant density of the liquid decreases. Right? That phenomenon is called effective density. Right? Now we can see this. Now, if you haven't seen this, we can see this. If we pour a glass of water onto another basket of water, right? When water is poured, we can see a white color water bubbles are coming up. So that is water bubbles. Sorry, white color air bubbles are coming up. They are air bubbles. Sorry? Happening? Sorry? I didn't get it. Carbonate water? No. They are, that's a different thing. That is not air bubble. It is carbonate by mixing carbon dioxide or something like that. But this is about air bubbles. Air bubbles. Usually we can see this near waterfalls. Have you seen near waterfalls? At the point where the waterfall is falling, at the very bottom, where the waterfall is falling, at the bottom of the waterfall, the color of water is white. Now, otherwise, water is colorless. No? If we can see white waters, which means that is mixed with air bubbles. We can see white waters, air bubbles are mixed only. Otherwise, water is colorless. If we are seeing water in a white color or whitish, means air bubbles are mixed. Usually, bottom of a waterfall, and even if you pour a glass of water, like when we pour, we can see a white color air bubbles on the other basket. Right? That is air bubbles. Right? Okay, so this is what is happening. This phenomenon is called effective density. This phenomenon is called effective density. Okay. Okay. First, take this down. Take this down. Finish. Okay. Below this, write down. Below this, write down. Write down. When air bubbles are mixed. When air bubbles are mixed. Write down. When air bubbles are mixed. When air bubbles, when air bubbles are mixed with a liquid. When air bubbles are mixed with the liquid. When air bubbles are mixed with the liquid, its density decreases. When air bubbles are mixed with a liquid, its density decreases. Its density decreases. When air bubbles are mixed with a liquid, its density decreases. Its density decreases. This decreased density, this decreased density, this decreased density, this decreased density due to mixing air bubbles. This decreased density due to mixing air bubbles. This decreased density due to mixing air bubbles is called effective density. Is called effective density. Is called effective density. Is called effective density. Right? So in that statement, highlight or underline, air bubbles are mixed. First line, air bubbles are mixed. Air bubbles are mixed. Highlight or underline, air bubbles are mixed. And then density decreases. Highlight or underline, density decreases. highlight or underline, density decreases. Right? Okay. Now look at here. As I told you, as an example, right? Now if this is a waterfall, if this is a waterfall, right? If this is a waterfall, bottom of the waterfall, there are waterfalls. Bottom of the waterfall, the color of water in bottom of a waterfall is whitish. Right? That is because there is mixed with air bubbles. Right? So therefore, here definitely this density is definitely less than 1000 kgm minus 3. This is less than density of water because air bubbles are mixed. Air bubbles are mixed. Right? So this is a popular example of this. Right? To determine effective density, don't write this, look at the board. To determine effective density, we have an equation like this. Effective density, look at the board, don't write. Effective density can be written as 1 cubic meter minus. Now, water bubbles are mixed, no? So, therefore, from 1 cubic meter minus the volume of water bubbles. Because the reason is actual density is defined for 1 cubic meter. Because the unit of density is kgm minus 3 kilograms per cubic meter. So, actual density is defined for 1 cubic meter. Actual density is defined for 1 cubic meter. From 1 cubic meter, now what is the mix? Therefore, subtract the volume of air bubbles. Subtract volume of air bubbles times actual density. Times actual density. This is called, right? This is called the equation of, we have only one equation for effective density. So therefore, wherever you find an effective density, this will be the only equation finding effective density. This will be the only equation to find. We have only one equation for effective density. Right? Okay. Now, as an example, write down example. Don't write this example. Write down example. Example. White color water at the bottom of a waterfall. White color water. White color water at the bottom of a waterfall. White color water at the bottom of a waterfall. White color water at the bottom of a waterfall. Right? White color water at the bottom of a waterfall. Right? And take this down. Take down the diagram. Take down the diagram. Okay. Then take down the equation and highlight the equation. 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 Question? Yes. Sorry? Yes, yeah, bubbles are there. Sorry? Destroy. Again, it comes back to say. Right? So if there are no air bubbles, right? Again, it will be at 1000 now. If we consider water, again it will be at 1000. But when air bubbles are mixed, then it is less than. When air bubbles are mixed. Okay, tell me equation effective density equals 1 cubic meter minus volume of oil times actual density. Okay, now listen. Listen. This is the impact of effective density. Now, as I explained, effective density is the phenomenon of decreasing density of a liquid when air bubbles are mixed. Right? Effective density is the phenomenon of decreasing density of a liquid when air bubbles are mixed. Right? So usually this happens at the bottom of a waterfall. Right? When water is fallen from the top, right, we can see white waters, right, white color waters at the bottom of the waterfall. So which means air bubbles are mixed. So therefore, definitely the density of the liquid here at the bottom of the waterfall is less than 1000. Right? So impact of this is this. Right? We know upthrust is, listen, we know upthrust is 0 G. Thrust is 0 G. Thrust is 0 G. Where V is the immersed volume, rho is density of liquid, and G is the acceleration. Now let's say a person tries to swim around this bottom of the water. Right? Now when a person is swimming, this is how forces are balanced. Now if this person is swimming, right, listen to this explanation. If this person is swimming, thrust and mg is balanced. When a person is swimming, right, this is not visible, this upthrust and mg is balanced when a person is swimming. Now the impact of effective density is when density decreases, thrust decreases. Right? When density decreases, thrust decreases. When thrust decreases, this force decreases. When that decreases, compared to upthrust, mg becomes heavier. Mg side of mg becomes greater. So therefore, even if that person is an expert swimmer, there is a possibility of sinking. There is a possibility of sinking. That is not the fault of the person. That is due to effective density. So that is why there are more fatal accidents or fatal events down the bottoms of waterfalls. That is the risk that has. We will be discussing about the upthrust and the impact of upthrust in Archimedes principle in the coming parts. This is just to give you an idea. The impact of effective density. When there is an effective density, we can observe it by white waters. Right? If we can see white water, which means there is an effective density. Right? So therefore, now let's say by default, density of water is 1000 now. When the average is, let's say that density decreases to 800 minus P. With that, the upthrust decreases. When upthrust decreases, mg becomes higher, mg becomes greater. So therefore, even when the person is an expert swimmer, the possibility of sinking is higher. Because always we have practice to swim when you need to swim. Right? For that natural condition, our body is practiced. Then our body is naturally practiced to that natural limit of mg for equilibrium. But when mu decreases, mg becomes greater and the possibility of sinking is very high. So therefore, keep that in mind. Keep that in mind. That is the risk we have, if we are swimming around the bottom of a waterfall, that risk is there. Right? There is not an inability of the person, no? There is not an inability of the swimmer. Right? It is because of this. Upthrust doesn't support the same way it supports in normal. Thrust doesn't support the same way it supports in normal way because density is less. Right? So therefore, even fatal accidents can happen. Right? So you also have heard that there are more news here and there going. This person got died while swimming around this, like that, right? The physics behind that is this. Physics behind that is this. Otherwise, that is not a supernatural thing or misery. It is not a mysterious thing. Right? The physics behind that is this. So only if we swim around the bottom of a waterfall, they are dynamics. Right? Always if we swim around the bottom of a waterfall, there are dynamics. We have a higher possibility of sinking. We have a higher possibility of sinking with the effective density. So if you have to calculate the effective density, this is the equation of effective density. Effective density is 1 cubic meter minus volume of particles times actual density. So therefore, effective density is always lesser density than the actual density. So we will see this impact with the calculation next. Right? Okay. Moving on. Moving on. You have a question? I thought you were raising hand. No? Okay. Take this down. Write this down. This is a calculation. Write this down. Air bubbles are mixed. Air bubbles are mixed. Air bubbles are mixed. Air bubbles are mixed with water uniformly. Air bubbles are mixed with water uniformly. Air bubbles are mixed with water uniformly. Full stop. Air bubbles are mixed with water uniformly. Right? Full stop. Volume of an air bubble. Volume of an air bubble. Volume of an air bubble. Volume of an air bubble volume of an air bubble is 1 cubic millimeter. This value. Volume of an air bubble is 1 cubic millimeter. 1 cubic millimeter. Here, volume of an air bubble is 1 cubic millimeter. And concentration of air bubbles. And concentration of air bubbles in the liquid is this value 2.5 times 10 to the power 8 per cubic meter. 2.5 times 10 to the power 8 per cubic meter. This value 2.5 times 10 to the power 8 per cubic meter. Right? If actual density of water is, if actual density of water is 1000 kgm minus 3, if actual density of water is 1000 kgm minus 3, if actual density of water is 1000 kgm minus 3, determine effective density of the area Determine effective density of the area. Determine effective density of the area where air bubbles are mixed. Determine effective density of the area where air bubbles are mixed. Determine effective density of the area where air bubbles are mixed. Determine effective density of the area where air bubbles are mixed. Determine effective density of the area where air bubbles are mixed. Okay. Okay, give it a try. Give it a try. What is concentration, by the way? What is concentration? You are chemistry students. What is concentration? Don't know? Ah, you are ICD. What is concentration? Yeah, right. That same idea. Right now, if you look at the unit level, you can get an idea. Concentration of variables, number of variables per cubic meter is given. So, if you are a chemistry student, concentration is not a new word. Right? In chemistry, always you are using the word concentration, no? Right? Concentration, number of moles, different things, volumes, densities, right? And in chemistry also, mixtures are also there, right? Right? So similar idea, same thing. Mixtures are also there in chemistry, right? So I know there are both ICD and chemistry students. For chemistry students, concentration is not a new word, right? So even if you are doing ID, you are doing physics here, right? Concentration is this. This is actually number of variables per cubic meter. Number of variables, it's a number of variables per cubic meter. Right? This is the volume of an atom. Right. And here also you will get an answer as a number. So once you got the answer, put that to the chat box, online students, and the physical ones, you can say it out loud. Put the answers. This is the only equation we have to determine an effective density. Okay. Meanwhile, since revisions are asking about registrations, right? This is the procedure. You have to get registered to the class. Our website is lms.mathlab.lk. Right? Even if you are an online student or a physical student, right? Registration process is same. You can register yourself through this, right? You can navigate to this, and there you can select the class and you can register yourself, right? This for Navy students. And if you got any questions in the sense, any doubts, technical difficulties or something like that, in my flyers and in the group also, you can see two numbers, right? The first number is my number and the second number is MATLAB hotline. You can contact any of two numbers for technical clarifications. Right? So if you have any other questions, you can contact any number uh, if you need anything. Right? And since some students is asking about the previous recordings, if you need to get previous recordings, the procedure is this. When it comes to free seminars like today, right? Free seminars. When it comes to free seminars like today, you can find the free seminars in my YouTube channel as well, right? Because I'll be uploading in the sense I'll be live streaming all free seminars in YouTube as well. Therefore, you can find all free seminars in my YouTube channel as well. Right? It goes as Pasindu Sandaruwan Physics. Right? In my YouTube channel also, you can find it. And if you need to purchase the previous month, right now as an example, let's say you need to cover circular motion. Now last month we covered circular motion. Now if you need to cover circular motion, then what you can do is, in that case, you have to register yourself. Now the first day of circular motion is also uploaded to YouTube. First day are there, right? First day was an open seminar, free seminar. So therefore, it was there. But if you need the full lesson of circular motion, what you can do is you can register yourself. You can purchase that particular month. Once that month is purchased, you can access our recordings through this. Right? So that is how it goes. Right? I hope it's clear enough. If you have any other questions, you can ask meanwhile. You can ask meanwhile. Yeah, I see some students are getting answers. Good, good. Others? Yeah, I can see some of you are getting answers. Others? You. Now, try to apply this scenario to this equation. Try to apply this given scenario to this equation. Right? Volume of unlayable is given. Volume of unlayable is given. And concentration is number of layers per cubic meter. Think about units. Think about units and apply the equation. Right? Think. So give it a try. right? Others, answers, any answers? Others, online students? Zoom, YouTube? What are the answers? From effective density, this is the only type of questions you are getting, huh? Right? Right. And last Saturday, we had the MCQ discussion of circular motion. Right? I saw most of you were joining, right? And if there are any students who didn't join uh, to that class of MCQ discussion of circular motion, right? That was actually a YouTube live that was open, right? But since we finished circular motion last week in this class, right? And after that, I scheduled that discussion of MCQs of circular motion, right? You were there, right? So if you uh, were not there for that class of circular motion MCQ discussion, right? Please go through it again and try those questions, right? Please go through again and try those questions. And in that YouTube live, I have pinned a comment uh, to the tube, right? I have pinned a comment. In there, you can see a link, and through that link, you can get the tube. So once you get the tube, you can go through the recording, or you can go through the video at any time, and you can try those questions, right? So try all the questions because I discussed different types of circular motion questions. They are very important. They are calculations, statements, other arguments, combinations of circular motion with vectors, combinations of circular motion with potential motion, right? There are different types of questions, right? So therefore, if there are anyone who didn't watch it, right, and if anyone who didn't join the live stream, right, this is a kind reminder to you to check that out as well. Okay, now the time is enough. What are the answers? Any answers? Time is enough. Look at here. Time is enough. Okay, look at here. Concentration is the number of air bubbles per 1 cubic meter, right? So here also I have 1 cubic meter minus volume of air bubbles, right? Per 1 cubic meter, right? Then, see, we can apply in the equation. Now, 1 air bubble is, right here, 1 air bubble is 1 cubic millimeter. 1 air bubble is 1 cubic millimeter, right? And there are this much of this number of air bubbles per cubic meter, right? Now, if I apply in the equation, right? Let's say effective density is rho dash. Usually we call rho dash for effective density. Right? Then 1 minus volume of air bubbles now, right? 1 air bubble is 1 cubic millimeter. 1 cubic millimeter. Millimeters to meter. What's the conversion? Millimeters to meter. 10 to the minus 3. Millimeters to meter. 10 to the minus 3. Then cubic means 10 to the minus 9. 6 cubic millimeter. Millimeters times millimeters times millimeters. Millimeters to meters is 10 to the minus 3. First 3. 10 to the minus 9. Right? So volume of 1 air bubble is this. Right? And volume of all air bubbles in 1 cubic meter is, concentration is this, times 2.5 times 10 to the power 8. Right? This is volume of an air bubble. This is number of air bubbles. Right? volume of an animal into number of animals. It gives total volume of animal per cubic meter. Right? Times actual density. Actual density of water is 1000. Actual density of water is 1000. Actual density of water is 1000. Right? Now simplify. Simplify this. 1 minus 10 to the power minus 9, 10 to the power 8 means 10 to the power minus 1. Right? 2.5 means then 0.25 times 1000. Right? So that is, this is 0.75 times 1000. Right? So that is 750. That is 750 kg minus 3. Yeah, I show the correct answer in chat box. Put 750 kg minus 3. 750 kg minus 3. Seven hundred and 50 kg minus 3. And as I told you, since 2-3 weeks, soon I'll be conducting another live session, a live seminar on graph plotting for A-level physics, right? So it covers everything about graph plotting for MCQs and structured essays, right? The date is not fixed yet, but sooner once I can fix a date, right? Sooner I'll be conducting that, right? And I won't be doing that same session again in the class because I'll be conducting that as an extra class, right? For graph plotting, and when we consider the amount of marks out of 100 for graph is around 15. There are 10 MCQs coming in, 50 MCQs from graphs, and other than that, some other graphs are coming in structured essays and essays, right? So altogether, for graphing, we have around 15 marks out of 100. 15 is a very huge amount. 15 is a huge amount. Only for graphing, right? So therefore, there is a must-have knowledge on graphing. So soon I'll be conducting that session as an extra class. So therefore, I'll be conducting a YouTube live session, right? Where anyone can join, and there I'll be discussing everything about graph plotting or the knowledge of graph plotting you need for A-level physics, right? And you can secure that 15 marks for graph through that session, right? So I'll be giving you all updates through my Telegram channel and other WhatsApp communities. So stay connected to them if you need to get updates, and through the YouTube channel, Facebook, and other WhatsApp community, Telegram channel. These are the main 4 sources I'm using for updates, right? So sooner I'll be conducting that, right? Yes. So this is the impact. When Avogadro dynamics, always the actual density decreases. When Avogadro dynamics, density decreases, right? So this is the impact. Now, any swimmer, even though he or she is a champion of swimming, right? There is a huge difference of upthrust between 1000 and 750. That is less. So this is like 3/4 of the upthrust. That is 74,000. Therefore, with that, even though that particular person is a champion, he is an expert of swimming, right? The possibility of sinking is higher with the lateral density. So that is the impact. So as physics students, what you have to know is, right? As physics students, what you have to know is, right? If you see uh, if you see water bodies, so if you see uh, what we call water surfaces with white water. White water means air bubbles are mixed, right? If you are going to swim there, right, know the risk that you are going to take. Know the risk that you are going to take, right? That is the risk you have, right? That is the risk you have. So as physics students, you have to know it, right? Otherwise, if you are sinking there, that is not supernatural thing. That is not misery, right? Right? That's it. That's it. Now in Sri Lankan context also, in Sri Lanka we have like numerous waterfalls. They are very famous for uh, fatal accidents. Right? In near some waterfalls, there are boards also put like don't swim near the waterfall. And in some waterfalls, I have seen that the death count is also mentioned sometimes. Right? That is because of this. Right? So I'm not saying that only reason is effective delivery. Right? But if someone is swimming around, try to swim around the bottom of the waterfall, this is also a very highly impacting, very highly impacting, right? Otherwise, there are some other, I mean, there are some other possibilities as well. The person is having, let's say, cramp or something, so it can be, he or she can be sunk on water. Or if that person is stuck between a stones or rocks or something, can be done. Likewise, some other reasons are there. But even if that the person is a fluent swimmer, experienced swimmer, even if he is unable to swim, and if he is sinking, right, this is a very highly probable reason. Very highly probable reason. Right? So as physics students, you have to know this. Right? Even if someone asks about this kind of a phenomenon, you should be able to explain as physics students. Right? So just know this much on this is due to effective density. Okay? So likewise, you will do you know. Let's say you have a colleague, a friend of yours doing arts, and he is saying that so don't go there, don't go there, you will get sunk if you're gonna swim there, and there is something inside water, something like that. To say that there's nothing inside water. The physics behind that is effective density. So just know that water bubbles are air bubbles are mixed with water. So therefore, density is less. Density is less. Therefore, that is why the possibility of sinking is high. Okay, that's enough. Any questions? Any questions? Oh, okay, mention this with a red pen. Mention this with a red pen. With a red pen. Strike mark and mention this. Right? After? Sorry? Thrust is there everywhere if we have an inverse volume. Still upthrust is there. Upthrust is right. Put an asterisk mark and write down density of a liquid decreases. Red pen, using a red pen. Density of a liquid decreases. Density of a liquid decreases. Density of a liquid decreases. Density of a liquid decreases when air bubbles are mixed. Density of a liquid decreases when air bubbles are mixed. Density of a liquid decreases when air bubbles are mixed. Density of a liquid decreases when air bubbles are mixed. Density of a liquid decreases when air bubbles are mixed. Right? Okay. Any questions before moving on? Quickly. Any questions up to here before moving on? No? Online students? Any questions about the parts we discussed so far in hydrostatics before moving on? Any questions? Online students, physical students? Any questions? Is it all clear? Okay, no questions, no? Fine. So we are moving on. The next heading, next heading, hydrostatic pressure. Hydrostatic pressure. This is one of the mostly contributing parts for the rest of the hydrostatics. Right? So this is the start of one of the mostly contributing parts for rest of hydrostatics and hydrodynamics both. Right? Hydrostatic pressure. Hydrostatic. Hydrostatic. Hydrostatic pressure. Hydrostatic pressure. Hydrostatic pressure. Hydrostatic pressure. Right. Hydrostatic pressure. So as the word suggests, now this is about hydrostatic means they are non-moving liquids. No? Now this is about pressure of non-moving liquids. Pressure of non-moving liquids. Right? Okay. Below that, write this down. Then I'll explain. First, write down this point. Then I'll explain. Write down the point. Let's consider. Let's consider. Let's consider. Let's consider a liquid column of. Let's consider a liquid column of. Let's consider a liquid column of let's consider a liquid column of cross-sectional area cross-sectional area capital A, cross-sectional area capital A, like this, cross-sectional area capital A, and height simple h, and height simple h, and height simple h, and density of liquid, and density of liquid, and density of liquid rho, and density of liquid rho, and density of liquid rho, and density of liquid rho. Put a comma, and look at the board. Stop all your work and look at the board. Now this is the next most important thing here on earth. Right? Look at the board. Right? Now this is a liquid container. This is a liquid container. Right? This is a liquid container. Right? And from this liquid container, look at the board. From this liquid container, right? I'm going to consider, look at the board. I'm going to consider liquid column of height simple h and cross-sectional area A like this. Right? So let's say this is point x of the liquid. Let's say this is point x of the liquid. Right? Look at the board. Now with this, I'm going to prove this. With this, I'm going to prove this. So therefore, you have to know this proof. Right? Now I'm going to draw a magnified view of this liquid column here. Magnified view of the liquid column. A magnified view like this. This is a magnified view of the liquid column. A magnified view of the liquid column. Right? Now, if I draw a magnified view, this is the liquid column I consider. And I told you, cross-sectional area of this liquid column is A. height of this liquid column is h. Density of the liquid is rho. Right? So if this is A, this is also A. If this side is A, this is also A because there is a uniform liquid column. Uniform liquid column. A very small liquid column. A very thin, very small liquid column. Right? Now we are going to prove the hydrostatic pressure. We are going to prove the hydrostatic pressure. Right? Okay, first tell me what's the general equation of pressure? I'm not asking about hydrostatic pressure. First tell me the general equation of pressure. What is the general equation of pressure? Force over area, which area? Oh, cross-sectional area, no. Perpendicular area, right? Like that, you are be very specific, huh? Right? There is not force over area, right? Force over perpendicular area, right? Force over perpendicular area, right? That is the general equation of pressure. No? So I'm going to start from that. I'm going to start from that. Look at here. Look at the proof. Look at the proof. Look at the proof. Look at this proof. General equation of pressure is force over perpendicular area. But as an equation, we are writing F4 by A. That is true. But you have to know the exact terms. Which force is perpendicular area. Right? Okay. Now, force. Only force acting here comes to the liquid column. Comes to the liquid column. If there is a liquid column has its own weight. No? That's a liquid column. This substance is having a doesn't matter whether it's a solid or liquid or gas. It has a right. Therefore, this weight of the liquid column, this weight of the liquid column, so this area. Now I have selected liquid column like this. I have selected the liquid column like this, right? And weight of the liquid column at some bottom cross-sectional area like this. Because this is having that is acting downwards, very downwards. Yeah, that is acting very downwards. Right? So therefore, force acts on this is mg. Force is mg, right? Over A. Perpendicular area is right. And we know m can be expanded as 0, right? From this equation we know, so that rho, we know rho equals m over v. So therefore, at any time, mass can be written as 0. Right? At any time, mass can be written as 0. At any point, mass can be written as 0. At any point, mass can be written as 0. Right? So therefore, I can expand this mass. Look at the board. I can expand this mass as volume into density. No? So mass is V rho G over A. Is that clear? Is that clear? When comes to volume, volume can be expanded as, right? Known things, volume can be expanded as how? Using cross-sectional area. How? The volume can be expanded using cross-sectional area. Cross-sectional area into length, right? Volume means cross-sectional area into length. Cross-sectional area into length. Right? So the other equation I'm using here is volume can be written as AL, cross-sectional area times length. Volume can be written as AL. AH, yes, AH. General equation is cross-sectional area into length. Length here is the height H. Therefore, now I can expand this V. I can expand this volume mass. Area times length. Length is actually height here. H. So that is AH now G over H. Is that clear? Right? Volume is AH. Now A to A cancels. A to A cancels. Right? And HOG remains. And HOG remains. And HOG remains. Right? HOG remains. So this is how hydrostatic pressure is proved. This is how the hydrostatic pressure is proved. Right? So I know that most of you know this equation from all over. Hydrostatic pressure is HOG. Right? So it is proved using the general equation of pressure like this. Hydrostatic pressure is HOG, but there is also proved using our general equation. Right? Specifically for hydrostatic pressure, we can use HOG. Right? So this is how the HOG is proved. Okay, now, right? Okay, now start from here. Take down the diagram and take down everything up to here. Take down everything up to here. Take down everything up to this point. HOG. And these are the used equations for this proof. These are the used equations. If you are using different colors to mark these heights, forces, and everything, you can use those colors. Now, hereafter, after this proof, we will be moving on to pressure riding through liquids. Pressure riding through liquids. So, after pressure riding through liquids, like one of the main parts you need to know, you need to be aware about hydrostatics, will be covered today. Right? Pressure riding. Because after pressure riding through liquids, all other parts which are coming up in hydrostatics are building up with pressure. Right? So therefore, all the foundation things, fundamental things about hydrostatics will be covered during the session, right? So that's why I always emphasize you to grab everything from the beginning, right? Or if you grab all the things from today, when it comes to the second day, next week, right? It will be nothing because second day is building up with these learnings, and third day is building up with the previous learnings. So likewise it goes. That's it. That is how a normal flow of a session is come. So here also that's it. Understood? Take down the proof. Okay. Now from this the obtained equation is this. Right? So after this, and below this, right? Again mention this. Delta P equals H rho G. And highlight the equation. Delta P equals H rho G and highlight the equation. And then we are going to introduce terms delta P H So G likewise. First write down the equation and highlight. Take down the equation and highlight. Take down the equation and highlight. O square, right? Highlighting means you can always spare. Finish? Okay. Introduce terms, delta V, delta V. Introduce terms one by one, delta V. Pressure difference of liquid column. Pressure difference of liquid column. Delta P. Delta P. Pressure difference of liquid column. Pressure difference of liquid column. Then H. H. Very important. Very important. H is not just a height. That is vertical height. H is vertical height. Not just a height, vertical height. Now I put using a vertical height here. So it is vertical height. Underline the word vertical. Underline the word vertical. Vertical height. Right? Not the height, vertical height. Vertical height. So density of liquid. Density of liquid. Density of liquid. G, gravitational acceleration. G, gravitational acceleration. Gravitational acceleration. Right? Vertical. No pressure difference. If there is no vertical height, no pressure difference. Right? If there is no vertical height, that's the idea. If there is no H, delta V becomes 0. No pressure difference. Right? Okay, look at here. Look at the board. Look at the board. Now, according to this two, when H increases, pressure difference increases, no? Right? When H increases, this is the equation. Now, this is a proved equation. When H increases, pressure difference increases. Right? So, therefore, H increases when we go down the liquid now. H increases when we go down the liquid. Downward the liquid. Right? Therefore, the idea here is this. Look at the board. Very important. If we are going down the liquid, always it will be writing as plus HOD because pressure increases downwards. Pressure increases downward with increasing H. But if you are coming from bottom to top, H decreases. When H decreases, if you are coming from bottom to top upwards, minus HOD. Minus HOD. So here onwards, these two are again going to be very vital for the upcoming pressure analysis part. Right? Use a red pen. Use a red pen. Red pen. And write down. Put an asterisk mark and write down. When writing pressures through liquids, when writing hydrostatic pressures through liquids, when writing hydrostatic pressures, when writing hydrostatic pressures, when writing hydrostatic pressures to liquids, put a comma and write down this below. Downwards, this is moving downwards, plus HOG. If we are moving upwards, minus HOG. And highlight those squares. This is going to be very important for the coming up parts here onwards. Now we are about to go into pressure writing. Right? About to go into pressure writing. Right? Okay. Hereafter, we will be discussing few examples how we are going to write pressures in liquids. Right? Hereafter, you will be seeing some examples, few examples, how we are going to write pressures to liquids. Right? Okay. So before that, any questions up to here? Any questions up to here? Any questions up to here? Online students? Any questions up to here? Quickly. Zoom, YouTube. Any questions up to here? Anything to clarify? Any questions? Anything to clarify? Any questions, students? I need a quick response before moving on because our next part is a very crucial part in hydrostatics, that is about pressure writing. So before moving on to pressure writing, first tell me if you have any doubts up here because we will clarify and go. Quickly. Students, quickly. Sure, go. Clear. Others? Clear. Right? So it seems it's clear up to here for everyone, no? Right? It seems it's clear up to here for everyone. Right. Okay. Write down. Right. Now hereafter we'll be discussing few examples on writing pressure. Okay. As an example, write down. Example means we will be doing few examples. Example. Then example, write down. Write down. Take this down as a question. Right. Example question. No? Take this down as find out pressure at find out pressure at find out pressure at find out write down write down find out pressure at point X. Find out pressure at point X in following scenarios given. Pressure at point X in following scenarios given. In following scenarios given. Pressure at point X in following scenarios given. And within brackets, consider atmospheric pressure. Consider atmospheric pressure. Consider atmospheric pressure. Consider atmospheric pressure as P naught. Consider atmospheric pressure as P naught, like this, P naught. Consider atmospheric pressure as P naught, like this, P naught. Consider atmospheric pressure as P naught. Okay, listen and look at the board. Listen and look at the board. Is the follower again very important thing here on words, right? Here on words, for all the liquids, we are going to consider the density as rho, right? And atmospheric pressure as P naught I gave you, right? Okay. Rho number one. Rho number one. This is the first scenario. Take this down with me. Now this is a test tube. Right? So in the test tube, liquid is put like this. Liquid is put like this. And here this is point X. Now in each scenario, I'll be marking a point as point X. I'll be marking a point as point X. Take it down with me. Take it down with me. And let's say the height from here to here is H. Take it down with me. And we will be considering this density as rho. We will be considering this density as rho. Take it down with me. Take it down with me. Okay, look at here. Look at here. First one. First one. Look at here. Now, in each scenario given, I'll be giving you few scenarios, several scenarios. In each scenario, I'll be marking a point as X. So we have tried pressure at X. Right? Now, from HOG equation, if I write it again here, HOG is not pressure. HOG is not pressure. That is pressure difference. That is pressure difference. That is very important. No? Most of the students are messing up with HOG, thinking that there is pressure. There is not pressure. There is pressure difference. Delta P equals HOG. Not P equals HOG. There is delta P equals HOG. Right? So therefore, my equation is this. Look at here. My equation is this. Delta P equals HOG. Delta P equals HOG. Right? There is not pressure. There is pressure difference. Delta P is pressure difference. Right? So therefore, always we have to start from non-pressure point. Always we have to start from a non-pressure point. Then the difference can be written using HOG. Clear? Okay. Listen. If we have any surface which is open to atmosphere or any surface which is open to surroundings, right? That particular surface feels atmospheric pressure. Right? If any surface is open to atmosphere, for that particular surface, atmospheric pressure is exerted. As an example, now I am open to atmosphere. Right? My skin is open to atmosphere. So each and every point of my skin, my body, feels atmospheric pressure. Right? Each and every point of your body feels atmospheric pressure because we are open to atmosphere. So likewise, if there is any surface, listen very carefully. Okay. Okay. Right? So what I was telling was, if any surface is open to atmosphere, it feels atmospheric pressure. Now, I'm in the atmosphere, right? My entire body is open to atmosphere. So each and every point of my skin, my body feels atmospheric pressure, right? For you also that's safe. For these desks, doors, boards, anything, since they are open to atmosphere, they feel atmospheric pressure. Likewise, right? In conclusion, any surface which is open to atmosphere has atmospheric pressure, right? Now this surface is open to atmosphere. This surface is open to atmosphere. So therefore, it has atmospheric pressure. I considered and I asked you to consider the atmospheric pressure as P naught. I asked you to consider atmospheric pressure as P naught, right? So likewise, if we are to write the pressure, always we have to start from a non-pressure point, right? We have to start from a non-pressure point, right? Now my non-point is P naught, right? Look at the board, first one, look at the board. Now starting from P naught, see, starting from P naught. Now I am at here, look at the board, look at the board. Stop all your work and look at the board, right? First question, first explanation. P naught means now I am at this surface, right? If I need to reach X, I need to come down the liquid distance H no. Coming down means plus H rho G. Coming down means plus H rho G. The distance, vertical distance coming down is H, right? Vertical distance I am coming down is H. So therefore, this is plus H rho G. If vertical H distance is came down, now I am at X. Now I'm at X now, I'm at X, which means this pressure equals pressure at X. Pressure at X is written as Px, pressure at X. Right? So this is how this equation is used. This is how the equation is used. Right? We have to start from a known point. Explaining again, listen. We have to start from a known point, and you have to go through the liquid to the target point. You have to go through the liquid to the target point. Right? Now, P naught means we are at the surface. If we need depth, we need to go vertically downwards. The distance H downwards means plus distance H rho G. Pressure difference is H rho G. Now P naught plus H rho G means now we are here. Here means we are at X. So that equals Px. So likewise, start from the known point and keep writing pressures until you are reaching the required point. Then at that required point, equate that pressure to the pressure at X. This is how pressure is written. Is it clear? Right? Now hereafter, we will be seeing, you will be seeing different scenarios to write pressure under these examples. Right? Clear? Clear now? Take it down. First one, take it down. Ask questions if you have anything. Ask questions if you have anything. Ask questions, ask any question actually. If you have anything, ask any question. HOG, gravitational acceleration, that is coming from the proved equation. Huh? Sorry?
So G, we reach X, right?
Right? From HOG, the pressure difference of this height H is represented. Then from P naught plus HOG means the pressure difference is added. So we are here at the pressure at X. Right? Understood, right? With the red pen, mention this below. Mention this below with the red pen. Mention this below with the red pen. Put an asterisk mark like this, and mention with the red pen. Mention any surface open to atmosphere. Any surface open to any surface open to atmosphere. Any surface open to atmosphere any surface open to atmosphere any surface open to atmosphere has atmospheric pressure has atmospheric pressure. Any surface open to atmosphere has atmospheric pressure. Right? Go to the scenario. Scenario 2. Go to the scenario. Second one. Second scenario. Again, this is a test tube. And the liquid is inside the test tube like this. This liquid is inside the test tube. And height of this liquid is L. And X is here. Right? Density is rho. Okay. Try this. Try this. Second scenario. Try it out. Try out the second scenario. Try out the second scenario. Quickly. Now, once you get this, now we can easily write down pressure differences. Correct. Good. Correct. Good. All next ones. Finished? Finished? All next ones. Now, as a habit, always mark atmospheric pressure if you have surfaces open to atmosphere. Right? As a habit, mark it. Now, this surface is open now. Right? So, atmospheric pressure is here like this. P naught. Right? So, start from that known point. P naught. Right? Now, I need to reach this point. I need to reach this point. Now, I need to come upwards a distance L. Coming upwards means minus HOG. Coming upwards means minus HOG. Minus. Now, the height is L. So, that is L rho G. Now, we are here at this air surface. Now, if there is no liquid, which means there is air. There is confined air. This is confined air. Confined. There is confined air. Right? At air surfaces, pressure at any point of an air surface is same. Now, as an example, in this room, right, pressure at any point is atmospheric pressure. In liquid surfaces, pressure changes point to point. But in air surfaces, right, pressure remains same. So, therefore, if I reach here means that is same as the pressure at the air surface, right? Which means we at x. So, this is equals to Px. This is equals to Px. P naught minus L rho G. Correct. Good. Understood? Right. Mention this with the red pen. Mention this with the red pen. Pressure at. No. Now, finally, we are here. No? Finally, we are at here. At here means at Px. So, that is equal to Px. Right? Started from here. Pressure difference is minus L rho G. Now, we are at here. At that point means that pressure is equal to Px. Right? With red pen, mention this. Pressure at any point of pressure at any point of pressure at any point of a same air volume. Pressure at any point of a same air volume. Pressure at any point of a same air volume is same. Pressure at any point of a same air volume is same. Same air volume is same. Right? Third one. Try this out. Third one. Try this out. Try this out. Okay, X is here. Try out. Now, after today's session, now all foundation you need to know about hydrostatics is done now. Now, if you are confident about everything that we discussed up to this point, which means foundation is done. Now you have got the 100% foundation of hydrostatics. If foundation is firm enough, then easily we can build up uh, the rest of the parts in hydrostatics. That's the idea, right? And by the next day, if you can't remember what you have done in today's class, then it is not going to work, because always it is going to be built up, right? It's going to be built up step by step, right? Everything is connected. So therefore, now, even if you understood everything today, by the next week, if you can't remember what is done today, and if you are behaving like you are hearing these things for the first time, then it's not going to work, right? So after today, now if you understood everything today, after today, please go through these things again and again, and uh, make it thorough, make that knowledge thorough, and come to next class. Then easily you can do the next class as well. Yeah, what's the answer? Yeah, right. Finished? Finished? T naught plus L cos theta rho g. L cos theta, L log cos theta. Online. P naught plus L cos theta rho g. P naught plus L cos theta rho g. Okay. What about YouTube? Okay, you are there, right? All right. Now again, start from the non point. Non point is here. This is open to atmosphere. Now, as I told you, also habit, always mark pressure at the non point, open surface. Open surface. Right? Okay, now we are starting from here. Starting from here, P naught. Right? H in HOG is not the height, that is vertical height. That is vertical height. Now, vertical height is from here to here. Vertical height is from here to here. This is the vertical height, right? Now, if you use the triangle, if this is L, beside this component is L cos theta. So therefore, this becomes L cos theta. This side becomes L sin theta, but we don't need. So therefore, I'm not going to write L sin theta. I just need the vertical height, no? Otherwise, this is actually L sin theta. This is L sin theta, but for my calculation, it won't be, right? Now, from here to X, I need to come down a vertical distance of L cos theta. Coming down, no? So it determines the sign. Coming down means plus. Plus. Height is L cos theta. Height is L cos theta rho g. Now we are here. Vertical distance came down. So we add x, that is px. Very easy. Understood? Next one. 4. 4. 4. Yeah, what about px? What about px? Check again. Check again. Online students. Yeah, I see some correct answers. Good, good, very good. I see some correct answers in online students. Yeah, very good. Very good, very good. Right. Let's see. You guys. Correct. Correct. Okay. So known point is here, open to atmosphere. So here we have atmospheric pressure. Right? Okay, now starting from P naught. Starting from P naught. Now I have to move from here to here. Right? So what's the vertical distance move? What's the vertical distance move? Zero. There is no vertical distance. That is a horizontal distance. There is no vertical distance. That is a horizontal distance. So horizontally, there is no h. Since there is no h, no pressure difference. Zero. That is actually 0 times rho g. This is how that comes. 0 times rho g. Now we are here px. So therefore, p naught equals px. P naught equals px. This is a very important takeout. We have to learn from here. Very important takeout. That is, right? Same level pressures at a static liquid is same. Same level, same horizontal level. Na? Same level means same horizontal level. Pressures at the same level of a static liquid is same. Right? So if there is P naught throughout this in the same horizontal level, that is same. Right? Okay, write down and mention this with a red pen. With a red pen, put an asterisk mark and mention this. Pressures at pressures at pressures at points in pressures at points in pressures at points in a same level pressures at points in a same level of a static liquid same level of a static liquid same level of a static liquid is same sorry are same right pressures at what did I say pressures at points in a same level of a static liquid are same right are same that is a very important learning after this point so therefore just know that there is no horizontal pressure difference in a static liquid only a vertical pressure difference there is no horizontal pressure difference there is no horizontal pressure difference understood right next one next one next one next one try it out try it out Finished? Online students? No answers? Online students? Others? Correct. Oh, correct. Correct. Online students? Okay, right here. Now the known point is this. This is open to atmosphere. The known point is this, right? So we can start from that point. P naught, P naught. Now I need to come down the distance h through the liquid. Coming down plus, right? Distance is h. So h rho g. Now I'm here. I came down and now I'm here. Right? Now I need to move horizontally from here to here. Now these lines are for my reference. These curves are for my reference. Now I need to move horizontally from here to here. But we know that there is no pressure difference in a static liquid horizontally. No pressure difference. Which means if I'm here, which means this pressure is same as the pressure here. Right? So without writing that zero, because now we know that, right? Without writing that zero, now if I'm here, that pressure is same as the pressure here. Now from here, we can go upwards. Upwards means minus a distance h rho g. Now we add the air medium. Pressure at any point of air medium is same. So x is also in the air medium. So therefore this is px. Right? So if needed, we can simplify this bit. P naught plus rho g can be taken out. Simple h minus capital H equals px. We can simplify a bit. Fine. Okay. Is it clear? Right? Online students, is it clear? Online students, is it clear? Yeah? Quickly, quickly. Right? Okay. Now listen. So here we discussed 5 scenarios, and this was about hiding pressure, right? And there are other types of applications from hiding pressures are also coming up, right? Other types means using these pressure hiding. There are some other types of applications, not just to hide pressures, but to find heights, angles, and several things can be done, right? This is not the end of applications of hiding pressures, right? This is just the start of applications of hiding pressures, right? Okay, now listen. Now we have come to one milestone, and from this, all the fundamental knowledge and the foundation, basic knowledge that you need to have in hydrostatics is done, right? All the foundation is done, right? Now, from today's session, if you understood everything up to here, which means your foundation is firm enough, right? Your foundation is firm enough. Now, next day onwards, listen very carefully. Next day onwards, now we are moving towards the other types of applications of pressure and the other parts which are coming up in hydrostatics, right? And everything will be based on this foundation knowledge we gathered today, right? So therefore, go through everything before coming to next class, right? Otherwise, it won't be useful even if you understood everything today. If you can't recall what is done today when you are coming to the next class, it is not going to work out, right? So So therefore, go through everything again before you are coming to the next class, right? So next day plan is we'll be proceeding in hydrostatics towards the other types of applications. So which means we are moving towards the advanced applications in hydrostatics. We are moving towards advanced applications. Now from here, all foundation you need to have for all the hydrostatics and throughout hydrodynamics is covered from here. Foundation, right? Foundation is done, right? And for online students, you will be getting the tube before the next day. You will be getting the tube for the session before the next day, right? Tubes will be posted by this week, so you will be getting the tube before the next day. And for you, you will be getting the tube from the right at the door. And next day will also be a full day with hydrostatics. For hydrostatics, it will take around 4 days to cover everything for hydrostatics, right? This is not that small lesson. It takes around 4 days to cover everything. So next day we are moving towards the other advanced applications, pressure, and there are some other parts coming up in hydrostatics, right? Mainly air separators, U tubes, and there are different parts coming up, right? So those are the parts which are coming up, and that will be the next day plan, right? And since there are new students, again I'm recalling that if you are registering to the class, if you are willing to register for the class, make sure that the address you are using when you are doing the registration in LMS is your home address, because we will be posting all tubes to that home address that you have entered in the LMS, right? So therefore, make sure that is correct. So we will be posting the tubes to you by this week, and you will receive the tube by the next day, before the next class, right? Not by the next day, before the next day, before the next class, right? So that is the next day plan, right? So any other questions before winding up? All good, online students? Zoom, YouTube, Zoom, YouTube. Any questions? Any other questions? Any other questions? Is everything clear from today's session? Is everything clear from today's session? Is everything clear from today's session? Right? Now, even if you need to go through the recording again, now since I stream this through YouTube, at any time you can visit my YouTube channel and go through the recording as well, right? Now, for all free sessions, that opportunity is here now. I mean, now onwards, that opportunity is there for all free sessions, right? Now, at any point, if needed, I mean, if needed, or maybe for a friend of yours, if there is needed, free sessions will always be available on my channel, right? So that chance is also there, right? And we'll be getting the tube before the next day, and after next day we'll be proceeding with the rest of the hydrostatics, right? No questions, clear? No questions? No? Right, good, good. Okay, so which means you have grabbed everything from today's session, right? So which means now your foundation of hydrostatics is done, right? This is the foundation, right? If your foundation is done, now that's a good sign for the second day, because second day will be based on the foundations here, right? So that is how always, not just hydrostatics, everything in physics is building up. That is how the steps are, right? Okay. So since there are no any questions, now I'm going to wind up the session, right? If you have anything related the subject matters or any other things, you can contact me through my personal number, or for technical issues and other issues, you can contact the MATLAB hotline as well, right? Yeah, no questions, no? All right then. So then let's wind up the session here, right? Let's wind up the session here. See you all in the next class. Go safe and stay safe and work hard, right? Goodbye and good night. Welcome all, welcome.